Hi, I'm Orlowski-Scherer, and today I'm going to present some work on the mass-richness scaling relation of the MaDCoWS cluster catalog as calibrated with the ACT CMB telescope. The work that will be presented in this talk has recently been published in a paper at this link below. So I'm going to start with a quick overview of large-scale structure and clusters. So this is a timeline of the standard cosmology of the universe. On the left, we have the Big Bang. And after the Big Bang, the universe is filled with hot, dense, and homogeneous plasma. Sometime after the Big Bang, the universe undergoes a period of rapid growth that we call inflation, during which it grows exponentially in a very short period of time. And then as the universe continues to expand, it cools. Eventually, it cools enough that the photons in the plasma decouple from the plasma, and the electrons recombine with the protons to form neutral hydrogen at about 375,000 years after the Big Bang. The light is then emitted as the CMB. The CMB photons then free stream through the galaxy, through the universe, excuse me. Concurrently, matter is collapsing to form structure. So what is the small fluctuations in density in the plasma imparted by inflation grow under the influence of gravity and pressure to form larger and larger structures. At some point you form stars, and then you form galaxies, and these galaxies coalesce to form clusters. And of course, the non-luminous matter, the dark matter, is also coalescing at the same time. Since this is ongoing as the CMBs are streaming through the universe, that growth of structure can become imprinted on the CMB photons, specifically as the photons pass through a cluster. And then we're over here on the right in the present day. So just one thing to emphasize is that we like to think of this as a hierarchical model of structure formation. So on the right here is a dark matter simulation showing a nearly homogeneous cube of dark matter that grows under the influence of gravity to eventually form these large structures, which are clusters here. And the important thing is that we form small bits first and then larger bits. And specifically, the rate at which this formation occurs is very sensitive to your cosmological model. So if you have a particular model, like say, lambda CDM with Planck cosmology, then you can test whether the amount of structure that you see at a given time in the universe concords with that cosmology that you've proposed. And one of the neat features here is that even a relatively few number of very, very large structures can rule out a cosmology. So, a single cluster at 10 to the 17 solar masses would rule out lambda CDM. Now we don't, or Planck lambda CDM. Now we don't see that, so that's good, but it only takes one. So to sort of summarize, what we need is a picture of the amount of structure, which we'll quantify by the amount of clusters that we see as a function of time, and we need to know how many at what mass, above what mass we see at each time. Right. So how do we actually go about detecting these clusters? Well, there's a number of ways. You can do it optically. You can do it with the Sunyaev-Zeldovich effect, or you can do it in the X-ray. And for all of these, you have to think carefully about what your selection functions in redshift and mass are, as these functions are these methods of detection. All have their own selection functions that cause you to see certain clusters better and not see other clusters. And so we're just showing in the right here a picture of El Gordo, one of the largest clusters detected. In the top left is optical, top right is IR, bottom left is an X-ray detection, bottom right is SC. And so in addition to understanding the selection functions of the clusters, we also need to be able to measure their mass. It's not enough to just count how many clusters there are at a certain time in the universe. You also need to know how massive they are. We're going to focus on how to do this in the optical and SZ, but one important thing to know is that fundamentally the SZ masses that we measure for a cluster are measured via the X-ray. So what we have here is a scaling relation where we have the measured Y signal, which is a measure of the SZ signal on the Y-axis, and on the X-axis we have the mass of the cluster as measured by an X-ray experiment, which directly probes the mass of the cluster by measuring the amount of photons due to dust and gas in the hot dust and gas in the cluster. And you can see that there's a fairly tight relation here between the two with relatively little scatter. So what this allows us to do is calibrate our SC measurements. So if we have an experiment like ACT and we measure a bunch of clusters, Compton Y signals, and then we go and measure their mass with an X-ray experiment, we can build the scaling relation. And then if we want to know what the mass of a cluster detected by ACT is, we just have to measure its Compton Y, and we can use this relationship to estimate within a reasonable precision of a few percent what the mass of the cluster is. One sort of important note is that optical surveys, much like SC surveys, do not return masses on their own. So you have to calibrate their masses some way. One way to do that is to make a mass richness scaling relation. So naively, you would expect that the mass of clusters would scale with the number of member galaxies, and for theoretical reasons, we believe that that's probably true too. So if we have a optical catalog of galaxies and we have SZ measurements for those catalogs, even if those clusters aren't detected in the SC, we can measure their mass richness scaling relation. What I mean by that is if we have a map of the Compton Y that you created with a SC sensitive experiment like ACT, and you can just go to the location of a optical cluster, measure the SC signal there, and infer a mass from it. So you can see that's what is done here on the right for a limited number of clusters, and you can see that the scaling relationship is a lot messier. And one additional thing to notice here is that the scaling relation is specific to an optical survey in their definition of richness. What is richness? It's essentially a quantification of the number of member galaxies, and it has to do with the particular filtering scheme and counting that the cluster survey chose to adopt. Gonzalez 2019 published an IR formally selected catalog of high redshift clusters that they called the MaDCOWS cluster catalog, and they did a preliminary calibration of the scaling relation using a small subset of those clusters. The goal of our work is to extend that to the full, or as much as we can, MaDCOWS cluster sample using ACT-SC data. So this is what the MaDCOWS survey looks like. It's the massive and distant clusters of Ys. So as the name implies, these are clusters that we detected using Ys. They're color cut to restrict their redshift, and they use limited spectroscopic follow-up to calibrate photoz's for most of the clusters. They range from about 0.7 to 1.5 in redshift, and there's about 2,800 of them. Of those, about 1,600 are in the ACT footprint, and of note, only about 100 of those are co-detections, meaning that they're detected both by ACT and by MaDCOWS. We believe that the primary cause of this is a relatively complicated selection function for the MaDCOWS survey, as well as a very low average mass compared to the ACT mass threshold. So as you can see, the average mass is quite low at about 1.6 times 10 to the 8. 1.6 plus or minus 0.8 times 10 to the 14 solar masses. This is in good agreement with a CMB lensing measurement that was done recently. So moving on, how do SZ surveys work? Well, they look for a spectral distortion in CMB as photons pass through the hot gas in clusters. They can be inverse Compton scattered off of those that hot gas, and they will have a spectral distortion imparted in them. And so, as I mentioned previously, you can calibrate this relationship using X-ray studies. The trade-off, this method has the sort of nice feature that you get it in for free, in quotes, when you do a CMB survey, but it has the trade-off that it's very low resolution compared to other frequencies. That particular CMB survey is ACT, the Atacama Cosmology Telescope. It's a 6-meter off-axis Gregorian telescope. located in the Atacama Desert. It's a 3-degree field of view, and it observes at 90, 150, and 220 gigahertz, with 28 and 41 gigahertz observations upcoming. Of note, we only use 90 and 150 gigahertz to do our SC measurements. So just to give you an idea of what ACT gives you over Planck alone, on the right here is a Planck map, and you can see the lack of small-scale structure due to the limited resolution of Planck. Most notably, you have these red points popping out, which are point sources. And then if you look more carefully, you can occasionally see a blue or spot or a deficit like that. They're kind of hard to see. That's a cluster right there, most likely. So ACT recently put out their DR5 data release. It's included about 4,200 SC selected clusters, all of which had optical confirmation. It is the largest homogeneous sample of SC selected clusters to be released to date. We have them identified over about 13,000 square degrees, and it has significant overlap with optical surveys, which is allowing for lensing mass calibration, which is currently ongoing. On the right here, you can just see in megaparsecs a real space view of where all of our clusters live. So they go quite far out to about the Z of 1.9. All right. So as we mentioned before, we had this sort of scaling relation. So how did we do that? Well, we make a map of the centralized Compton Y, which is essentially a measure of the SC signal for a cluster. And the map is constructed such that each pixel records the Y0 value that a cluster would have if it were to be detected at a given location in the map. So then you simply extract the value of Y0 at the location of the MaDCOWS clusters and then convert it to mass in the same way that we convert Y0 to mass for our SC selected ACT clusters. The resulting masses are free of SC selection bias. In other words, they don't need to be deboosted, but they do contain other biases. And so what that actually looks like is you go from a picture like this with maybe 3 dozen clusters to a picture like this with after some redshift, after some cuts, about 1,000 clusters. And you can see that the picture has become much more complicated. There are, especially towards high richnesses, this general trend of richness of mass, or in this case, Y0 with richness, but there's an enormous blob of essentially undetected clusters here at very low Y0, and even some with statistically significantly negative Compton SC, which is not great. What we think part of the issue that we think is going on here is that the SC signal is being infilled by dusty and radio emission in the clusters. So the matched filter that's applied to the ACT 98 150 gigahertz map returns an estimate of Y0 based on the beam convolved filter profile and the shape of the SC spectral distortion, both of which are assumptions that are baked into the algorithm. And so if you have emission at 90 and 80, that is, 98 150, that is spatially correlated with clusters, that can contaminate your Y0 measurement. We call this infilling, since it has the tendency to cause a Y0 decrement to be, sort of removed or obliterated. We did a lot of work in this paper estimating the strength of this effect. We think it's probably about a 1 per 2% effect on average, meaning that the average cluster has about 1 to 2% less Compton Y than you would, we observe 1 to 2% less Compton Y than it probably really has, but there's a significant component with significant infill. About 10% have about 10% infill. The way that we first sort of detected this, by the way, is that we saw this excess in the 220 emission on the MaDCOWS clusters, which we later determined was dusty IR emission. And so one area of follow-up here is to have targeted observations with Mustang to an instrument on the Green Bank Observatory. So as I said, some of this info is due to IR emission. Using Herschel 600, 857, and 1200 gigahertz data, we fit a modified gray body to the emission from 220 through those Herschel bands. We did not detect significant excess of emission in the ACT clusters, but we did with the MaDCOWS. For the MaDCOWS clusters, we found a rest frame best fit temperature of about 28 Kelvin. And and a spectral index of about 1.9, which are both in line with other studies. And then our force photometry is, of course, corrected for this emission. In addition to IR emission, we also measured the radio contamination in the clusters. So we used radio fluxes from MBSS and VLAS to construct a simple polynomial model of this form for all of the clusters that are in both the MBSS and VLAS footprints from both ACT and MaDCOWS. We found a typical spectral index of about minus 0.9 for the MaDCOWS clusters and minus 1.2 for the ACT clusters, but there's a significant spread on those, as you can see. Similarly to the IR, we remove the radio contamination from force photometry. So if you actually plot out a histogram of what this looks like this. So you can see there's a significant fraction that don't have very much infill at all, but there's also, a few percent that have very significant infill. One thing that we want to highlight is that the exact amount of infill, as you might imagine, is extremely sensitive to the spectral index, which we're inferring from 1.4 gigahertz and 3 gigahertz all the way up to 90 due to the lack of any other supplementary data sets. So what's shown here is that, a small difference in your measured spectral index can lead to quite a large difference in the infill. Targeted observations that can better constrain the spectral index of these radio sources associated with these clusters is warranted in order to really nail down how strong this effect is. This is what the actual mass richness scaling relation looks like. We fit a mixture model which included a population which is normal distributed about the power law, which are clusters that scale according to the mass richness scaling relation. And we also fit a normal population, noise-like population, which is normally distributed about 0. Each data point has a fit weight, which is the probability of belonging to either those two populations, which is one of the fit parameters. And we found a power law slope kappa with a best fit of 1.84, which is in agreement with Gonzalez 2019, but quite a bit higher than the value of unity that you would expect for a self-similar cluster. We believe probably the dominant reason why it's so much higher than the value that you would expect is contamination of the richness measurement due to unviralized line of sight components to the clusters. So looking to the future, Simons Observatory is the next generation CMB observatory that is going to begin observations in the next 2 years. It will feature 1 large aperture telescope as well as 3 small aperture telescopes. It's going to put about an order of magnitude more detectors on the sky as compared to current generation experiments. We're going to have about 40,000 in the LATR and 30,000 across the SATs, with the capability to expand to more than 80,000 detectors in the LATR. The LAT and the LATR are the instruments primarily concerned with small angular science, so clusters, while the SATs are more concerned with large angular scales, mostly recovering B modes. And just from the SO science paper, here's some projections for our cluster survey with SO. We project about a factor of 5 increase in cluster counts, which translate to about 16,000 clusters for SO baseline and 24,000 for the SO goal at signal noise 5, greater than 5. We project to detect clusters to a redshift of 3, and we'll have about a sky coverage of about 40% for excellent overlap with upcoming optical and IR surveys. And you can read the science paper here for full details. So in conclusion, cluster abundance is a strong probe of cosmology, but it needs to be, you need proper calibration of cluster masses in order to actually achieve precision cosmology with them. Yeah, so I'm almost out of time, so thank you very much.